Greetings, differential equation scholars, and welcome back to the fourth and final installment of our discussion of the Cauchy-Euler equations. Way back in the first episode, we had a third order Cauchy-Euler equation, and I promised you that we would solve that. And we've been looking primarily at second order equations, but the same theory that we've been using for second order equations, we can extend to third or higher order equations. Again, we start with our assumption that y is equal to x to the m for this equation. Because we see that it's Cauchy-Euler, that gives us that y prime is m times x to the m minus 1. Y double prime is m squared minus m times x to the m minus second. And now, since this is a third order equation, we're going to actually differentiate one more time. And when we differentiate y double prime, when the m squared minus m multiplies the m minus 2, we're going to end up with m cubed times 3m squared plus 2m as the multiplier of x to the m minus third power. And so now we're going to take those expressions and we're going to substitute in the expression for y triple prime and the expression for y double prime and the expression for y into our original differential equation. And you can see I've done the substitution here. And then when we factor out our x to the m power, as we always do, what's going to end up happening in this particular case is that our the multiplier of x to the m power is going to be m cubed plus 2m squared minus 3m minus 10. That's, of course, a third degree polynomial. The auxiliary equation is a cubic equation now rather than a quadratic. Now, when you're faced with a cubic like that, the question, of course, is, what roots does it have? We can't use the quadratic formula directly. So you can use either some techniques from algebra to look for rational roots, or you can go to your handy-dandy grapher, and you can graph out that cubic polynomial to get a sense of what real roots that it might have. When you do that, your grapher is going to show you that this polynomial does have a real root at m equal to 2. You can see that from the graph there where the graph is crossing the axis at 2. So we know that we've got a real root at m equal to 2. You can verify that too if you substitute 2 into the cubic polynomial. 2 cubed is 8. Plus 2 times 2 squared gives us a total of 16, and then minus 6 minus 10. That does evaluate to 0 at m equal to 2. So 2 is definitely a real root of that cubic polynomial. And once we've found that real root, we can then go and use a technique like synthetic division to factor that out and find out what the remaining quadratic expression is in the factorization. And so I've done some synthetic division here, and we found out that it turns out that that cubic polynomial factors into m minus 2 times m squared plus 4m plus 5. Now, as we probably guessed from looking at the graph of the cubic polynomial, since it only had one real root, we probably surmise that that quadratic polynomial there, m squared plus 4m plus 5, does not have any real roots, and indeed it has complex roots. So we're going to take a look at those complex roots by using the quadratic formula. When we use the quadratic formula on m squared plus 4m plus 5, we're going to do the quadratic formula there and find out that we get negative 4 plus the square root of negative 4 divided by 2. And that's going to work out to negative 2 plus or minus I. We've got two complex roots for that quadratic piece of the auxiliary equation. So what did we end up with then? We've ended up with one real root at m equal to 2, and we have these two complex roots, negative 2 plus I and negative 2 minus I. So what does that give us for a fundamental set? For our first function, we're going to have y1 equal to x squared. That's coming from the real root. And remember that whenever you have complex roots, if you have a complex root of the form a plus bi and a minus bi, because they come in conjugates, then what's going to happen is your solutions that come from that are going to be x to the a power, where a is the real part, times either the cosine of b log x or the sine of b log x. And so in this case here, the b, which is the imaginary part, is just 1, because we have one I for our imaginary part of the complex number. So the multiplier of the log x is just 1 here. So x to the minus second, real part, times cosine of 1 log x, and x to the minus second times the sine of 1 log x. That's our fundamental set. And then we're going to form our solution to the homogeneous equation as a linear combination of those three functions. C1 times x squared plus C2 times x to the minus second times cosine of log x plus C3 times x to the minus second times the sine of log x. And that will be our solution to our cubic Cauchy-Euler equation that we started with. And I wish you well in your continued studies.